about the solid and continuum mechanics, like one deformation might be a valid configuration, the same deformation turned by 180 degrees might be a valid configuration of the solid. But obviously, if you interpolate between the two, you get to a state that's definitely not admissible in any sense for the problem. And then if you think about a lot of methods in PDE, and I'm not claiming this holds true for all of them, and they're extremely useful in any case, but if you think about a lot of these methods, like Galerkin or fixed point theorems, they often implicitly rely on this linear structure in a sense, on this global linear structure, or even on some convexity, both convexity in the sense of the set of admissible states, as well as convexity in the sense of the functionals involved. I mean, in this case, this would mean that this Fouché derivative would be some monotone operator, which it definitely isn't in continuum mechanics in general. If you don't do stuff like linearization or impose some smallness conditions on strains or stresses and do this stuff. But, so these methods work, but you always have to think about, okay, this is the specific problem I want to apply them on, and can I do this, can I do this not? How do I kind of get into a regime where it's working? So basically the thought that stood at the beginning of all of this is, okay, what about doing a variational approach? And I mean, there's the obvious classical thing, okay, you do your principle of least action. That's kind of what all physicists do. If you ask them, especially the theoretical physicists, if you ask them, okay, what's the physical model for this thing, they'll just write you a big Lagrangian, and then magically the critical points of this action functional you get from there will give you the equations. Well, the problem, of course, is in continuum mechanics in general, there will be no minimizers. And the reason we want to use the variational approach, of course, is to use the direct method, which gives us existence of a minimizer. I mean, but there is none. Like in general, this action functional isn't coercive. So you might try some mountain path stuff. I don't know. I'm not good with that. To get somewhere, but again, this is problem specific. So of course you need another approach. And next thing, of course, is a time stepping approach, and this has been well known. It's called minimizing movements. For some people, other people call it differently, of course. And for problems without inertia, what I'm going to call quasi-stationary or quasi-static, this works wonderfully. Like there's a stack of results in continuum mechanics, I think, that uses this method. And if you print them all out, this stack probably would go from the floor to the ceiling or somehow. There's so many of them. But in the inertial case, this approach is kind of problematic. And I'll show you the details in a few slides, because you generally don't get generic energy estimates. Like if, again, you consider the specific problem, you often get energy estimates for the specific problem. But in general, there's no one method that works. So the question is, now what? And maybe you need a different approach. And I think that we've found this different approach. So how is this talk going to be structured? So in the end, the final result we prove is about fluid structure interaction. But in the beginning, we kind of start with simple viscoelasticity of a solid. And from there, you can go one way, and you can add inertia, you can add the dynamics. That's interesting on its own. Or you could go the other way. You still could not use inertia, but add a fluid and do what I'm going to call quasi-stationary fluid structure interaction. And if you know how to do both in some specific way, then it turns out you can combine both and solve the full fluid structure interaction problem. And this is kind of the outline. So first we're going one way from no inertia to inertia. And there I'm going to try to convince you that this concept basically works for every problem where you understood the quasi-stationary, the viscoelastic problem effectively. And then on the other side, I'm going to show you how to combine Lagrangian and Lagrangian-Eulerian in this variational setting, where it works quite well, I believe. And then if you combine both, you go down to the end and solve the full fluid structure interaction problem. Okay, that being said, let's start at the top. So this probably might be known to many, how to do the minimizing movements. I'm still going, oh, sorry, that's one thing first. So before I repeat the minimizing movements, let's fix some first half of notation. So right now we're going to consider a solid, which will be in some reference configuration, which will be Q, some deformation, which always will be eta. Eta will depend on some indices, on time, and on whatnot, and this will kind of map into some general Eulerian domain, which can be all of Rn, or it can be some subset of Rn. And there are some important quantities that always occur, which are going to be the deformation itself, of course. There will be a set of admissible deformations, which I won't specify, but obviously the big thing in here always is injectivity. And there you have to put in some work, especially if you later want to add a fluid. There will be some elastic energy, which always will be E, and the dissipation in the solid I'll always model by some functional, which depends on deformation itself and on the movement. And this is kind of a big restriction, which is not necessary, but makes a lot of the stuff I'm talking about easier. So you can always think of this dissipation being too homogeneous in the second argument. So in a basic way, think of it as the first gradient squared with some slight parameters in front to make it physical. But yeah, that's not important otherwise. So yeah, let's go to minimizing movements. So we're trying to solve this quasi-static equation. So effectively, we're kind of trying to flow downhill with the energy, fighting against dissipation, and there might be some force in here. And the idea that goes back to the Georgi, I think, is to do the following iteration. So for you fix some time step, and then for any given eta k, you find the eta k plus 1, the next step, as the minimizer of such a functional. Where you say, okay, we're trying to minimize the energy, but of course there's a cost. This dissipation functional, I said it's quadratic in the second argument. This will, of course, start to grow if we go too far from eta k. And then there's some term involving the forces. And then you take this and you start to derive some properties. Of course, it's a minimum problem, so we try to find the Euler-Lagrange equation. And you find out, okay, that's basically backwards Euler, what you get there. So you might ask, why didn't we do backwards Euler in the first place? Why this minimization? Well, the key is that we get a natural energy inequality via this minimization. So if you think about it, since eta k plus 1 is going to be a minimizer of this thing, putting in eta k instead will always be worse. But if you put eta k in here, then here we have eta k minus eta k, here equally eta k minus eta k, and so those two terms will vanish. And you naturally get this inequality, which is close but not quite the physical energy inequality you would expect, but it's good enough because discounting this force term, which you need to estimate a bit against some other stuff, you can kind of telescope this thing, and it will give you a uniform estimate on the energy, and it will kind of give you a discrete integrated estimate on the dissipation. And then you do this, you kind of take the piecewise constant approximation of everything you have, and then from this piecewise constant approximation, you have your bounds, you use a compactness, and you converge to the limit in this equation and get a solution. And the final key thing about this method is you're minimizing over the set of admissible states, which I forgot to put here, I believe. So this is in E. So importantly, this means that your piecewise constant approximation also is always a function in the admissible configurations or admissible deformations or whatever your specific problem is. I mean, right now we're doing solids, but this works quite in general. And it's kind of going to be the key thing that we're always approximating in this admissible configuration. When you think about a lot of techniques like Galerkin, for example, there this can be a problem. Like you take your span of finitely many functions that try to span whatever you're doing, but then the linear combinations in there might not be admissible at all. You don't know. So if your set of admissible states, deformations, whatever, is quite weird, quite non-convex, quite undescribable, this is a useful method to do it. I mean, people use this to show gradient flows on metric spaces. Like not even with a linear structure at all, like with a vector space structure. Okay, now that we know how to do viscoelasticity, let's look at dynamics. All this so far was old stuff. Now let's try something new. So we try to generalize this to a problem of inertia. Okay, what's the first approach? Well, you just add another term here, try to somehow mimic what you did for the first time derivative with the second time derivative. At first glance, the scaling is a bit weird, but if you take this one and you try to calculate the Euler-Lagrange equation for your problem, of course, this has a minimizer, so this one is fine, then it's the correct approximation. Like, I mean, I hit the tau here because I didn't want to write the big discrete differential quotient. And I think the 2 here shouldn't be there also. Yeah, but otherwise you get the right Euler-Lagrange equation if you don't mess it up. But then the problem starts. Like last time we had this beautiful energy estimate. And now if we try to do the same trick again, we run into a problem. Because if we insert eta k for eta in this one here, then yes, this term drops. I ignore the force for now, but this would also vanish. But for the second one, you get this term. And this term has the wrong scaling. Because what you want to do is somehow say this times tau over tau to get some kind of discrete integral over here. But this doesn't work because this one will be unbounded. And physically this makes sense because right now you compare the solution that goes forward at a certain speed with a solution that suddenly stops. Like time still advances in a way in this thing, but you're comparing with the solution that suddenly doesn't advance. So it's kind of obvious that this doesn't work. And then you can try other workarounds. There's my slide. And maybe think, okay, what about we use the Euler-Lagrange equation to estimate this instead? Or the same thing would be, what about we don't compare with eta k, but compare with eta k plus the previous velocity times tau. In any case, you will have to estimate a term like this. And to estimate this one, you need the monotonicity of your energy, which in general for solid mechanics you won't have. So this one doesn't work. Like the trick obviously works. Like you do the stuff you always do. When doing your energy estimate, you kind of test with the time derivative. So it works if you're continuous. But if you're discrete, well, you need to know something about the energy. You can often derive some estimates even if you're not don't have a convex energy, but you're kind of close enough in a sense. But again, there's nothing generic. And so we thought about this for a long time, and I think Sebastian kind of jokingly even put out this idea after a long discussion, it was late in the evening or something, of kind of doing both discrete and continuous at the same time. And I looked at it, and yeah, if you do it the right way, if you think about it, it works beautifully. And the idea is what I'm going to call the time delayed equation. So, we had our time step tau, and now we have another, which is h, which isn't actually a time step in a traditional sense, but some short time. And we're considering a problem that's continuous in time. So where everything is continuous, like you have your correct time derivative here, but the second time derivative is still discrete with this h. And if you do it this way, and then just take this equation you want to solve and rewrite it a bit, like you throw this delayed thing over to the other side, then what you have here is basically the gradient of an energy, the gradient of some dissipation. This one is also the gradient of some dissipation, which of course blows up if you send h to 0, but it's still the gradient of some dissipation, because if you take dt eta squared over 1/2, you get this one as the gradient. And then you have this right-hand side, which also depends on eta. But the thing is, if t is small, if t is somewhere in the interval 0 to h, this here is initial data. It has to be, because then t minus h is negative if you start at t equals 0. And if this is initial data, then this here is the standard quasi-stationary problem with a force, with a really weird force and a weird dissipation, but still, it's a standard problem, you can solve it. And you get a solution on the interval 0h. And then you think about it, if you have a solution on the interval 0h, then on the interval h to h, dt eta t minus h will be a given right-hand side. So again, in a problem you can solve with the standard minimizing movements approach. And you iterate this again and again, and you solve this kind of time-delayed equations for long times. Now, of course, to do this, to use this, you need to show that not only, you construct this, but you also need to show that it's kind of a valid right-hand side. You need some energy inequality. But in fact, you can derive an energy inequality for the whole thing, because now this thing is time continuous. So now formally, we can test with dt eta. And now if we test with dt eta, well, everything is fine. We get the time derivative of the energy. This is where the too homogeneous nature of the dissipation comes in, actually. Otherwise, you would get the Legendre transform plus R. This way, you only get 2R. And then you get this weird term. But this one is no problem at all. Like, you multiply this one out. This is like dt eta squared, sorry, at time t, minus dt eta t minus h dt eta at t, but then you just use Young's inequality on this one, and you basically get a 1/2 of this term of a minus and minus 1/2 this term squared, which you throw on the other side, and then you get into the equation down here, which almost really is the physical energy inequality. Because now you have your potential energy, and it didn't do forces, but there would be a force term here, of course, as well. You have the actual physical dissipation, which has this factor 2 in it. That's a bit in the details. But weirdly enough, the kinetic energy is kind of averaged over an interval of length h. But at this point, this doesn't matter. Like, this gives you a uniform, good enough estimate. You get an L infinity estimate on your energy. You get this estimate here. And you can actually use this one together with the equation and kind of Aubin-Léon's argument to actually get strong convergence of dt eta and L2, which is good enough to then also have weak convergence of the second time derivative. Or not weak convergence, sorry, not weak. To write the second time derivative in a weak sense and have convergence of that, this way around. And the really interesting thing here is, I believe the interesting thing here, if you think again about this non-convexity, we never use convexity of the energy really, and also of the domain of basically admissible states. Our minimizing movements iteration never left us. And thus this time delayed approximation always for every time is admissible. And so we have an approximation, which is something that's already admissible, which personally I think is really useful in many applications, so that you don't have to worry about, okay, I have some constraints which I don't satisfy or have to relax some terms. And yeah, this basically gives you the first theorem, which kind of tells us, okay, if our energy and everything is nice with conditions I didn't show you, then we have a solution. And if we put injectivity as the big constraint on the admissible things, or rather we're in a Necas seminar, so obviously we put the CLE Necas condition as a condition on a solid, then we get that we have a solution onto self-contact. And this one is already in the paper in the archive, but then you can think about it some more. And I did together with Antonin and Giovanni. And the really nice thing is this self-contact or contact against the boundaries of your Eulerian domain is not the end of the method. Like, all this constructive stuff still works. And you're still in the admissible set. It's just, instead of an Euler-Lagrange equation, you have an obstacle problem. So you get a variational inequality at this point. Or alternatively, you get a Lagrange multiplier, depending on how you formulate it. And then you look at this Lagrange multiplier, and you notice that it has to be the physically correct contact force. And with this contact force, you immediately get, without putting in what the contact force is, it's just happening from the variation. With this, you get existence of this problem for all time with the physically right setting. Like, the example we were kind of thinking about is if you take a rubber ball and bounce it off the wall, it should bounce, and there shouldn't be any extra condition on this bouncing. You just should know that the ball itself is elastic and that it can't go inside the wall. And this turns out to be the case mathematically. Okay, so much about solids alone. Yeah, this I already said. Now let's ignore inertia again. Let's look at fluid structure interaction. Because if you think about all the stuff we did, it seems to be, if you understand this quasi-stationary problem, then you can try to apply this method to get to the dynamic. I mean, with what I showed you, you should be able to do it for every Lagrangian problem, if I tell you a bit more about the details, I guess. But the other interesting thing in fluid structure interaction, of course, is that if you think about it, you have to do something in the Eulerian setting as well. Because doing a solid in a Lagrangian way is kind of the obvious thing to do. But for a fluid, you don't really have a reference configuration. You can't follow every fluid particle. It's impossible. Instead, you have to have a fluid flow. So to limitation, I'm adding a new variable, which will be the fluid velocity v. It's kind of obvious. The interesting thing in this fluid structure interaction stuff is that now v is going to be defined on a varying domain. Whenever I change eta, I have to change the domain for v. You can make this mathematically much nicer if you think about it, that of course you can also look at the solid velocity in Eulerian sense. And then in this case, you get a velocity on all of omega. But mathematically, that's actually not necessary. And I mean, there are other problems people look at, like with thin shells, for example, instead of this bulk solid of same dimension, where you actually need to work with changing domains. Okay. Now we're trying to solve this quasi-stationary or parabolic, if you might call it that way, fluid structure interaction problem. So the evolution for the solid we already know. I mean, that's just this one. For the fluid now, I mean, what's stationary for a fluid? Well, effectively that's Stokes flow. I mean, you could argue about other things, but Stokes flow is definitely a good candidate. We're doing an incompressible fluid here, so divergence 0, which gives us a pressure, of course. And then we have to say, okay, how are the two coupled? And there, of course, we're looking at no-slip boundary conditions because that's kind of the fitting ones for Stokes. Again, you don't have to, it's just for this specific case we looked at. It makes things easier in some places, but it's never truly necessary, I believe. And no-slip boundary conditions in particular mean that we have this strange coupling because we have our fluid velocity at the boundary or at the interface, and we have a solid velocity. But the solid velocity is defined on the Lagrangian configuration, and the fluid velocity is defined on the Eulerian configuration. So there's this extra eta here, this coupling condition, which makes it nonlinear and which I guess, again, people have been in agony about. I mean, you can deal with it, but it's hard. But interestingly, in this approach, it turns out not to be hard at all. Yeah, more about that later. And then, of course, you have some higher order force balances, which I'm not writing down because even in a simplified setting, these are complicated terms. But the nice thing is we actually never have to write them down. I'll tell you in a second. Another thing is, since we're quasi-stationary, the only thing that matters really is the deformation. Because like there's no time derivative in here. There's no initial data on velocity. I mean, we never had any for this quasi-static evolution. It's just looking at where am I in the energy landscape, how do I get down from here? But for the fluid, there's no dTV. So V is always only depending on what is eta doing at the moment, in a way. So effectively, for this problem, the fluid just acts as an extra dissipation. And this will also show mathematically. Because if we try to do minimizing movements on this thing, then we can just try the same approach. Okay, given some deformation eta k, we now try to find the eta k plus 1. With this, of course, we try to find the discrete fluid velocity because that's the difference quotient. And we also try to find Vk plus 1. And the idea is that the solid is dissipating energy as before, and the fluid should dissipate the energy in the same way. And for the Stokes equation, this dissipation is the symmetrized gradient. So we just add this term here, and there are some force terms, which kind of look like they obviously should look. And then, of course, we have this coupling condition again. I mean, we had the same before, the velocities should match. So right now we're claiming the discrete velocities should match as well. Then you take this, and then you take the Euler-Lagrange equation. And if you do variations only in the solid, if you only vary eta in the interior, then of course this term has no contribution. You get your solid equation. Equally, if you vary only in the fluid, this term has no contribution, so you get your fluid equation. So both of these are weak, of course, in actuality. But if you vary both of them at the same time, then you can only, and then you vary close to the interface, then you can only vary such that this coupling condition still holds for all your variations. And automatically from there, because this is actually the physical energy balance, kind of, or part of it, you automatically get the right force balance at the boundary. You don't even have to worry about this, which I personally believe is really useful. Yeah, so there's that. And then the other thing is, in what we did before, it turned out to be right, that in the energy, the current position, or the position, or the deformation is implicit, sorry, other way around, while in dissipation it has to be explicit. But then since this fluid part kind of behaves like a dissipation, this means the right way to do things here actually is to also have this domain explicit. And this automatically means that the coupling condition needs to be explicit. And this is really nice because this means we have to do a minimization for a fixed domain only, which saves a lot of pain, I believe. And leads to the right force balance, of course. I mean, that one we checked. And then, yeah, of course, you take this, you do your usual stuff, you do your energy estimates, which work in precisely the same way I showed you before. And now you think about, okay, we had these two different things, how do we combine the two? And there is one more final ingredient. So what are the equations we want to solve? So now we have this force balance for the solid, and I drop the density here and for the fluid as well. And there may be some sign error in all the slides. I'm not sure about this one. And then we have the Navier-Stokes equation for the fluid. Oh yeah, and one thing I forgot in this last minimization, because we were minimizing over divergence-free vector fields, we get the pressure automatically as a Lagrange multiplier. So in all the stuff you're doing here, you never have to worry about the pressure, because effectively what you're doing is you write your weak equation and you only test with divergence-free functions, and then this term doesn't occur, and only all the way in the end you say, okay, we can define the pressure operator by what's missing, as you can do. Okay, sorry, back to that. So we have the incompressible Navier-Stokes equation for the fluid. This is the one we want to have. So basically stuff from before. And then there's this stuff here, which is the material derivative. Because looking at the time derivative of a velocity in a fluid doesn't make any sense. Like if you fix a point in space and look how fast are the particles flowing through there and how does their velocity change with time. I mean, one particle doesn't know what the other guy did a minute ago flowing through the space. But if you combine these two, then effectively you're following the velocity of the particle and how this changes, which is much more sensible. And yeah, the rest is as before. And So the big question is, what is the analogon of the time delayed equation for a fluid? Because, like as I said, you can't really compare the velocities of a point in space at different times. You should compare the velocities of a particle. So what you need at this stage is a flow map. You basically solve the ODE of this flow V and saying, okay, for s equals 0, it should be the identity, then the s derivative should follow this one here. Like just, yeah, basically along the vector field. And then the difference quotient you want to look at is this one with this flow map. And the question is, well, can you do this? How do you get your phi? Like, you can certainly write this down, like put this term here on the right-hand side, and then do your minimizing movements iteration with this, because then it's going to be a force. But the question is, does this term always exist? Because, well, in general, it doesn't. That's kind of the obstacle. But the point is here, we can do it. And the interesting thing is we never have to solve this ODE. Like we construct phi instead. Because for every time step tau, we're just saying, okay, well, what's the next discrete version of this one? Well, phi 0 needs to be the identity. And then for the next step, we just update. Like we concatenate this one with identity plus tau times the current velocity. And the really nice thing is this is also compatible with boundary conditions. So if you look at phi of the, if you look at phi for a point on the boundary or on the interface, that's the thing, then wherever phi will map the point in the fluid along this interface, is the same point the solid will also move. And so in particular, phi will always map your initial fluid domain to your fluid domain a few steps later. And then, of course, the question is, well, okay, discretely we can write this down, but does it converge? And here the idea is that in the same way, I think it was hidden somewhere on the slides, I impose some extra regularity if h is larger than 0. On my solid, I can easily impose the same extra regularity on the fluid. And if I can do that, I can do the following estimate. So what is the Lipschitz constant of phi k in space only, not in time? I can estimate this as the product of all the Lipschitz constants of the function involved, which again you can estimate by this one, because that's the worst thing it can be. And then you say, okay, this is a long product, like infinitely many terms, well, not infinitely many, but unboundedly many, sorry. But well, a product, I know this arithmetic and geometric mean inequality. Well, let's write it this way. Why not? Like this is just a basic first semester inequality, or high school inequality, basically. And then you notice what you have. Because if you take this t from here and put it over here, then this is kind of a discrete time integral. And then you have 1 plus 1 over k times this discrete time interval to the power of k. And yeah, you know, this will get you the exponential. And so with this additional regularity, for which will depend on h, but so basically what you do is you kind of add to the dissipation some h times some really high gradient of v, but you don't care. Because if you send h to 0, this one will no longer contribute. But this one will give you an h-dependent estimate on this integral. And for now, h is fixed. And then you get a bound on this Lipschitz constant. And similarly, you can show that phi is volume preserving. And this allows you to have phi converging to something if you send tau to 0. And then if you send h to 0, of course, there will be no existence. Like this regularization is gone. And I mean, you know that for Navier-Stokes in general, there is no flow map. Like there are those strange solutions which doesn't allow it. If there would be a flow map, then like the Navier-Stokes problem would be solved. But the thing is, you don't actually need the existence, because the only place where this map phi is actually used is in this discrete difference quotient. And not the only place, it's silently used in a few other places, but that's the big one. And in this difference quotient, if you send h to 0, you don't want it. There shouldn't be any phi anymore, because like if you look formally at this difference quotient, you expect it, and this should be v, not u, by the way, you expect it to converge to the material derivative. And this turns out to be true. Like you need to do a lot more estimates. There's some Aubin-Léonce hidden in there, but that's more technical. But then you get convergence of this thing in a weak sense, in the way you need it. And then you've solved the full bulk fluid structure interaction problem, at least until the time of the first surf contact, with, well, the obvious thing that, I mean, people assume that for no slip conditions, if your solid is like nice enough, some C1 alpha, then there actually is no self-contact or contact of the solid with something else. Because of course there are some terms and conditions that apply. So in particular, what I didn't mention, but what makes a lot of the proofs much easier, is that we're going to assume our energy to be defined in W2Q for Q larger than N and coercive and everything, because if you do this, then in particular, you can choose your energy in such a way that a finite energy implies that the determinant is larger than 0 uniformly. I mean, I think I saw Stefan Krömer in the audience. This is of his paper with Healy, I think. I took this idea. So this makes things a bit easier, but then again, for the actual constructive stuff, there's no place where this comes in, except that a lot of calculations get easier. But in theory, I think you can just do it anyway. Your equation will look really weird, because I mean that's what happens. That's the old Bohr problem, that trying to minimize a solid without somehow enforcing these conditions gets you only an abstract kind of solution. But it's not an obstacle in the method itself. Yeah, about the dissipation being too homogeneous, I already talked. And again, you also need a Korn inequality on this one, but this one is known. And yeah, also regularity of the boundaries is nice to have. But a lot of this stuff here is to get a weak solution. Like if you're only interested in measure-valued solutions, like as a first step, they mostly don't need this stuff in such a strong sense. That's another thing. And even with these restrictions, this covers a large class of physically reasonable materials. And again, I stress like the space of admissible deformations and the energy. And I mean, normally they're taken to be convex or somewhat convex in a different sense, but in both senses, we don't need it in any place. There's some minty property hidden here, but without it, you still get measure-valued solutions. And I mean, my big claim is that you can use this stuff for any problem, really. We understand this quasi-stationary stuff. And we already started on some related things. So here's just a list of results that are actually already, at least in preparation, if not already on the archive. The first one was kind of, I mean, a short paper over Christmas, basically, I have to say, just to show what you can do with this stuff from a modeling point of view. Because if you say, okay, let's look at a different fluid structure interaction. Let's have solid and fluid somehow be less interacting. Like, why shouldn't they share the same domain? But if they share the same domain, then of course they hate moving at different velocities. Like, this gives you friction. So you take the model from before, you drop this interface condition to extend, you say your fluid lives on the whole domain, and then you just add an extra dissipation, which just says, okay, we take this relative velocity and effectively take this one squared and add this as dissipation. There's some geometry involved to make it physically reasonable, so there's some tensor in there as well, but otherwise you can take this. And then you do this, you do the same procedure, you immediately get existence, you get your equations from this initial Euler-Lagrange equation, effectively, and then just a few terms converging. And you notice it's really close to known porous media type equations, only that now the porous media itself can move. And yeah, you've modeled breathing two masks. I mean, that's kind of where the idea came from. It's obviously topical. Yeah, but it's a really nice illustration of the method, and probably the second paper is maybe easier to look at as the first one, mostly because it's shorter and the problem is easier. Then another thing we did is we looked at compressible fluids. This I did with Sebastian and Dominic Breit. And this is interesting as well, because if you think back to this quasi-stationary fluid before, the fluid there was purely dissipative, because an incompressible fluid doesn't have a state. Like, it has some velocity if you have inertia, but if you have no inertia, there's no state. But the compressible fluid at different times has different densities. So there is some state, and you need to transport this density. And this density gives you a potential energy of the fluid, which is actually the thing that gives you your pressure term in the end. But still, this works beautifully with this method, in particular because you have this flow map in your approximation that precisely tells you how the mass is transported. Actually, interestingly, at least it looks like it, actually you can't transport the density purely with this flow map. You actually need to disperse it a bit, otherwise regularity gets harder, which I didn't expect, and I think we can get around at some point, but we'll have to see. I mean, it's still in preparation. There might still be some changes. And then another thing with John Marco and with Sebastian, which is also interesting to look at, you can of course do the same analysis on this classic fluid structure interaction problem where you say, okay, you have a 1D beam on top of a 2D fluid, and this allows you to work with much nicer spaces, because now you can take your Q equal to 2, so W22, and this means, well, in this specific case we're looking at, means that the highest order terms are at least kind of quadilinear, which is of course really nice for convergences. And then we can look at, okay, what happens if we send the fluid density to 0, kind of in a vacuum, or what happens if the solid viscosity actually vanishes. Because for this bulk solid we had, you kind of need the viscosity in the bulk solid in order to make some things easier, not to get into measure valid solutions and stuff like this. But if you have a 1D beam on a 2D fluid, then every point of your solid is of course in connection with the fluid. And then what you kind of get is that your solid inherits the viscosity from the fluid in a sense. But yeah, this is also in preparation, work in progress. So I'm not going too much into details. And then there's a huge list of possible extensions that I've been thinking about, and where basically I think I know how they should be done or could be done, and it's just a matter of writing down the details. And of course, it's always the details that are the problem in the end. But still, you can think about, in this fluid structure problem, you think about general material laws. In particular, we had this too homogeneous dissipation, both for the solid and the fluid right now, but that's actually not needed. Like, you can take any convex dissipation functional, which, I mean, it's done in this quasi-stationary case all the time. And then in your equation, you get the subgradient of this dissipation functional, and you can model a lot of stuff with this. You could change the boundary data in the same problem. Like, there's nothing preventing us from using slip boundary, except that then you have to really work with changing domains instead of cheating around it, but it's still possible. You can even add some limited slip type conditions in your dissipation. Like, that's not a problem. It's all in there. You can just add another term to the dissipation functional that somehow depends on the difference in velocities at the boundary. And you can take this idea, and personally, I believe you can put it pretty much everywhere in continuum mechanics. Like, I've not tried it yet, but I don't see why it shouldn't work in thermomechanics. If you can add some, I mean, call it magnetoelastodynamics, probably should be also visco in there, if you add some magnetic field or whatever. I mean, people know how to do fractures in this quasi-stationary case, or at least know some ways how to do them, and then argue which one is the best. But you could add dynamics to that as well. You could do reaction diffusion. I mean, we had this contact bouncing result. You could add friction to that. I think I have an idea how this is quite possible with this method. Or you could do general mathematics. There's this big open question of numerics as well, because if you think about it, we had this strange model where we only get the energy estimate from a continuous equation. And so if you want to do a numerical approximation, maybe you want to take both time steps t, both time steps tau and h to be positive, and somehow move them to 0 at the same time, instead of first tau to 0 and then h to 0. And then it's not a priori clear what you can do there. Although I have to say, Sebastian and Antonin apparently have some preliminary results, at least for the specific problem and fluid structure interaction we discussed. At least that's what they've been telling me. And with that, I think I talked enough, and I would like to thank you for your attention.